Welcome back. Today we're starting a new unit, Unit 3, about implicit differentiation and related rates. This is going to be a fairly short unit that finishes up Chapter 2 in the textbook. These two ideas are closely related, but a little bit different than the rest of Chapter 2, the basic derivative rules. So to me, they sort of form their own units. I'm going to give you a moment to get everything set in your notes. I'm going to make the video pause, and then we're going to get moving. So first of all, so far, all we have looked at, finding derivatives of, but really understanding in general, are what we call explicit formulas. Formulas where we have explicitly solved for y. Things like y equals 5x plus 2, things like y equals sine x plus 5 over x. These are what we call explicit formulas because they're solved for y. And we can find the derivative of these things, getting the slope at any particular x value, and that's all well and good. What we're going to start looking at, though, are called implicit formulas. Things where we don't have the y solved for. For example, things like 2x plus 3y equals 6 is an example of an implicit formula. Now, if I want to find the derivative of this thing, hopefully you would think that the easiest thing to do is, well, just turn this into a y equals formula, turn this into an explicit formula, and then go, which would be exactly right. We'd subtract 2x from both sides, divide by 3, we would get an explicit formula. Then we can differentiate and use all of our basic derivative rules and all that stuff. However, what if I gave you an implicit formula like this? X squared minus 2y cubed plus 4x squared y plus 5 equals 0. And ask you to find the derivative, the formula that gives us the slope of a tangent line of that thing. Well, before we go on, let's just see what this looks like in the first place. It should be some sort of curve that we can find the slope of. So when you go to the website desmos.com, it brings up this home screen. Click on Graphing Calculator. And then you can type anything in here that it will graph. For example, if I want to graph y equals x squared, I'm going to type y equals x raised to the shift 6. The 2 gives me y equals x squared. That's not really what we want to deal with here. We want to try to graph that implicit formula that was given. So I'm going to type x raised to the second power. I need to use the right arrow to move out of the power. Now I'm going to say minus 2y raised to the third power. Again, use the right arrow to move out of here. And it's not going to graph it until I type the equals and then type a number at the end. Then I'm going to say plus 4x squared, move over, y, plus 5 equals 0. And I have my kind of different looking implicit formula over here with those three pieces like that. You can drag this around, you can zoom in, you can zoom out, and that's kind of how Desmos works. So after I give you each new problem moving forward in the next couple of videos that we try to then find the derivative, the slope of, and all that, you're going to type it into Desmos and just see what it looks like just because, I don't know, I think it's kind of interesting. So as we go through this section, you're going to have a chance to go into Desmos and graph these things and take a look at these interesting looking implicit formulas. Again, my goal is to find the derivative, the slope of this thing. I can't easily solve this thing for y, so we need a new method. First of all, our goal for all of this stuff is to find the slope. And we're going to use our notation dy
dx. I think I showed you that earlier, just told you it was a symbol for the derivative. We're going to start getting into that symbol a little bit more and what exactly that means. First idea, to find dy dx. We are differentiating, finding the derivative. We are differentiating with respect to x. Which is a fancy way of saying x is the independent variable. And y is a function of x. Even though in something like this, y is not clearly solved for, we can still treat it as a function of x. Then, our two big ideas. The derivative of x by itself is the same thing it always is just 1. The derivative of x is 1, just like it was in the beginning of the chapter. If we want to do the derivative of y, though, or a better way of thinking about this is when I have these formulas, I'm writing y, but it's going to be implied that y is a function of x. The derivative of y, or really the derivative of y of x, is y prime of x. Or I can use this new symbol we're going to kind of focus on in this section, dy dx. Take a moment and make sure all of that is copied down. So let me show you how this is all going to work. Our first example, I want to find the derivative of y cubed. Now, I'm not going to go through all the work that I'm about to show you for most problems. We're going to use some kind of shortcut ideas. But the idea here is I want to find the derivative of, so y cubed is really like saying y of x, that thing, cubed. And if I want to find the derivative of this, I have to go use the chain rule, because I have one function inside another function. My chain rule says I'm going to take the derivative of the outside. I'm going to say 3 times y of x, that thing, squared. But by the chain rule, I then need to multiply by the derivative of the inside. What's the derivative of y of x? Well, it's y prime of x. Now, this notation gets a little cumbersome. Instead of writing it out like this, I'm going to write it using a little bit of shortcut notation. The derivative of y cubed is, well, how do we do the derivative of a cube? We pull the 3 out front and subtract 1 from the power, 3 times y squared. Y, though, is really a function of x, so I then need to multiply by the derivative of y, and I'm going to use that other symbol, dy dx. This and this tell the same thing. This notation is just a little bit more compact. But I still have my 3. I still have my y of x squaring. I'm just calling it y squared rather than y of x squaring, but the of x is implied. And I have my y prime, or my dy dx. They're all there. This is just the notation that we're going to use. Let me show you 2 more of these, and then we'll start getting into some actual complete implicit formulas. Let's take a look at the derivative of x plus 3y. The derivative of x just 1. The derivative of 3y is plus 3 times the derivative of y is dy dx. And there I go. The derivative of 1 plus 3y is 1 plus 3 dy dx. Really what you need to realize is the derivative of x is 1, the derivative of y, dy dx. One more like this. Let's take a look at the derivative of x, y squared. I hope when you look at this problem, the product rule jumps out at you because I see a product over there. X times y squared, that looks like product rule. So I'm going to go and do my first times derivative of the second plus second times derivative of the first. Remembering when I do the derivative of x, it's just 1. But the derivative of y is dy dx because I'm using those chain rule ideas. So, first, x times derivative of the second, derivative of y squared. Well, the derivative of the square, 2y to the first. But by chain rule, I now need to multiply by the derivative of y. I need to multiply by dy dx. X times 2y dy dx is my first times derivative of the second. Plus second, y squared times derivative of the first is times 1. If I want to find the derivative of xy squared, I'm going to get this line. If this seems a little bit fuzzy to you, don't worry too much. I feel like as we move through the next several videos, you will start to pick this up. The bottom line with everything, though, is x is our independent variable. The derivative of x is 1. Y is our dependent variable. Y is not really y. Y is really y of x. What's the derivative of y of x? Y prime of x. So here, using our shortcut notation, what's the derivative of y? Dy dx. More soon.